We just proved a theorem about graph theory. What theorem did we just prove about graph theory? That was unexpected. Let n be a positive integer, and let k sub n be the complete graph on n vertices. The size of kn is, and my first vertex here. So remember, size is number of edges. The size of kn is, let's think about a kn. I have one. How many edges, if there are n vertices, how many edges have one as its smallest element? Not n. I'm going to have an edge 1, 2. I'm going to have an edge 1, 3. You agree? I'm going to keep going down and all the way up to n, and there are n minus 1. Then when I look at 2, I'm not going to need to count 2 again because I already counted 1, 2. And 2 is going to have edges. Well, how many edges are there here? N minus 2. And then as I keep doing this, eventually I'm going to get to the last one, which is going to be the n minus 1 is adjacent to 1. And there's only going to be 1 there. By the way, you see how this is also a triangle? Let's rewrite this in summation notation. And I have to be careful here. Now I have to be really careful here. So I have the sum from k equals 1 to n minus 1 of k. Do y'all see where I got that from? I got 1 very enthusiastic nod. Could you get like 3 very enthusiastic nods? Only if you agree. I'm not trying to force you into agreeing with me, but if you agree, will you clearly let me know why this is? So the first vertex has n minus 1 edges. The second has n minus 2 edges. And the last n minus 1 is only adjacent to n. Or I can use this formula, but I have to be careful because this is for n, and what I need is n minus 1. So what would t of m minus 1 be? It would be m minus 1 plus 1 times m minus 1 over 2. Or m times m minus 1 over 2. But that's all I need here, except here my m minus 1 was actually n minus 1. Or, if you don't like this way I've said it here, alternative theorem. In a complete graph on n vertices, there are n times n minus 1 over 2 edges. And it's like, this is so wild. So wild. Now I have another challenge for you. All right, are there any questions, thoughts, or comments about this so far? You believe it? So it's plausible. This is a really important thing. Being able to go from my summation to my b equals 1 to nb versus looking at it as b plus 1 times b over 2. How many operations does this take? If I'm evaluating this and I'm trying to count the additions, how many additions does it take? See, so let's do it. 1 plus 2 plus 3 takes 2 additions. 1 plus 2 plus 3 plus 4 takes 3 additions. And in general, this is n minus 1 additions. If I write it out, 0.5 times b plus 1. 3 what's? What are the 3 operations you see? This takes 2 multiplications and an addition.
Is that how a computer would immediately understand? So what
Well, I have no idea what Wolfram Alpha is doing. Well, Wolfram Alpha is doing whatever Stephen Wolfram is being told. You're asking what algorithm is being used to evaluate.
Yeah, when I type in the summation.
Oh, the computer does not know this. The computer does not know this. So do this experiment. Write out, please do this experiment. Define T1 of n as tot equals 0 for T in range 1n. I'm going to call this Q because I don't want T and plus in the same pseudocode. Tot equals tot plus Q, return tot. Y'all agree? And this, even though it says range 1 to n in Python, that actually stops it in minus. So do y'all agree that this and this are the same thing? And an alternative way would be to just do the multiplication. The program and the representation are exactly the same thing. And if you believe mathematics, there's a mathematical proof that that's true. So my challenge to you is to compare these two programs for large numbers. See, the mistake you're making when you ask Cordell's Wolfram Alpha doing is you're assuming, so this is the same function. This is what's called closed form. And the reason this is called closed form is the number of operations needed does not increase regardless of how large the number grows. So if you evaluate this for 1 billion, you still need 3 operations. So here's my challenge to you. Earlier, we looked at the sum from k equals 0 to n 2 to the k. Now this is even worse because not only here am I having a large number of additions, I'm having a large number of multiplications. Can you find a closed form for this? Well, what do we do when we have a problem we don't know how to solve? There are many different approaches. But one is we can start investigating and gather data. So let's call this b of n. So what's b of 0? It's just the sum from 0 to 0, 2 to the k, which is 2 to the 0, which is 1. If I look at b of 1, I get the sum from k equals 0 to 1, 2 to the k. It's 2 to the 0 plus 2 to the 1. If I look at b of 2, I'm just going to write this out. This is 1 plus 2. If I look at b of 2, this is the sum from k equals 0 to 2, 2 to the k. It's 2 to the 0 plus 2 to the 1, which is 7. If I look at b of 3, k equals 0 to 3, 2 to the k to the 0 plus 2 to the 1. And now I have to look and see. If I'm going to make a conjecture, I have to base it on something. I have to see, is there anything I can connect this to that I might recognize?